Okay, so I want to get around to chapter 58, Sockets, Fundamentals of TCP Networks, but before I do that, I was on my walk and I was thinking I really want to implement a client-server setup with Unix domain sockets that authenticates the caller's PID, user ID, group IDs, all that stuff. So I didn't see that in the books coverage, so I'm going to do that myself. So we'll say vim up a auth Unix domain server.c. We'll just do a main here. We can delete everything there. And I'm just going to stub out here this program. So we're going to unlink this socket, bind the Unix domain stream socket. So we bind, listen for new connections, accept those connections in a loop, and then we're going to create a pthread to handle each connection. Pthread, we'll just call this what do we want to call this function? You can call it what? Pthread func called, what do you want to call it? Handle connection. It reads the socket authenticated socket data for user, or we'll say PID, UID, GID, etc., and prints it out. It then performs an echo server service responding with everything the client sends. So I'll just get flesh out this C program. Just get AI working on that. Okay. Bam. Instead of doing read write, can you instead use the, what was it called? Man2 is called split. No. Man syscalls. That's not gonna help. Okay. Start with an S if you're thinking of it. Socket splice, using splice. Splice is called. Okay. Put that in there. Does not like that because we need an extra pound include. Man to splice. FCNTL. We don't have that already? Okay. FCNTL. Okay, let's continue reading here. Handle connection, void star, convert that into a file descriptor. Come on. Okay, build auth Unix domain server, auth Unix domain server C, GCC wall extra O2, pthread auth. Okay, looks good. And then we'll do the same thing for client here. Well, client might not need it. So you might be able to get away with not giving pthreads here. In fact, let's just comp that out for now. Just do a regular make. See if it runs. Build auth server. Okay. Let's open up our auth server. I just want to read through it real fast here. So our file descriptor that we listen on, I like declaring it in line instead of doing this shit. Yep, that's fine. Move it. I don't think we need these comments. It's pretty obvious. Instead of doing memset here, I'm going to do what we discussed earlier, which is like that. I think it's like that. And then that'll take away the need of doing that. Still have to do a string copy though. Yep. Bind. Yep. These exits, I'm gonna go with the standard lib constants, exit failure. Oops, did not do that correctly. Okay, so we bind and then we listen. Looks good. I don't like this is called listen FD. This should just be called FD. We'll do code rename, just call it FD. Oops, code rename FD, like that, yeah. Okay, so forever we do our accept. Client FD, that's good. I like to call this thing connection con FD. We then create our P thread. Okay. We just say, hey, detach, you don't need to join. Okay. And this will return exit success. Looks good. Now in their handle connection, get our thing, we fix our credentials. This is the thing that the ucred struct, which I wasn't really familiar with, but you can call get sock opt, and you say, hey, I want the sole socket is the level. SO peer cred. Okay, that looks good. We printf our cred ID, cred UID, cred GID. What is in this cred? I guess that's all we get. Okay. And then this thing creates a pipe. I don't know why we need a pipe. The fuck is it doing with these pipe stuff? Use it for splicing. Okay. So we create our file descriptors for splicing. And then we go into our forever loop. We have an out label that we can go to or break to. Probably go to. And then here, so this is socket to pipe. We say, hey, splice from the file descriptor to the pipe's right end, and then splice from the pipe's read end to the output file descriptor, back to the file descriptor. Why can't we just splice from the file descriptor to the file descriptor? Okay, and then here we go, remaining n. If m is less than 0, then there's an error, in which case we go to out because we can't break out of the while loop here. I mean, we can break out of the while loop, but we can't break out of the for loop. Client disconnected, and then close all our file descriptors and return null just to have something to return there. I mean, it looks good to me. So can you write me a reciprocal client that reads from standard in and writes to the server over the Unix domain socket? this client shouldn't use splice. It should just connect to the Unix domain socket and read from standard in and write to the socket. Why is he using splice here? So that's an EOF. Alright. Make build auth Unix domain server. Then over here, I'm going to jump to chapter 57, build auth client, foobar, hello. Then here, I'm going to do another jump to chapter 57, build auth Unix domain client. So this is totally different PID. Are Unix domain sockets the only way to get authenticated data using, what was this? Put this up here. Oops. Pure cred. AF netlink SCM credentials and send message ancillary data. On Linux, you can send struct ucred with a message over Unix domain sockets only. This mechanism uses SCM credentials. And send message only works in AF Unix sockets, which is Unix domain sockets as well. You can share file descriptors via send message plus SCM rights Unix sockets again. I'm good. Pretty much this is the only way of doing it. Getting authenticated credentials from the clients. Okay. Let's go ahead and tear this down. Cool. Oh, I didn't do my commit for chapter 56. I thought I did. Chapter 56 was socket introduction, which we did this morning, I believe. If we go to progress, this morning we started at 1149, which should have been not introduction. Okay, so that's why I haven't done a commit today, which is fine. I don't need to do a commit. Just wondering why it was added. Let's get add chapter 57. And then under get status, cd chapter 57. I actually want to vim the make file because I actually didn't need this. Make clean, make get status, get add chapter 57. Cool. So in here we have binding, make file, get ignore, that's all good. There's some ref stuff. Same thing there. Okay. Let's vim up the readme and we can mark that done. So that's like one of the big features of Unix domain sockets that, like, I'm surprised he didn't cover, which is that you can get the pure credentials from the socket using get sock opt, and there's no other way of doing that with any other type of IPC mechanism. So that's like a really powerful feature, and I know certain cloud software I've seen uses that to ensure that things are authenticated, that it's actually that PID that sent me this data, and so the kernel has told me that this is the PID that sent me that data, and so I can inspect that PID and find out information about it, and it can't lie to me, it can't spoof it. Okay. Chapter 58, socket fundamentals of TCP/IP networks. So this is mostly going to be a review for me. It's going to be another one that I just read through. I'm not going to probably do a lot of exercises for. So we are on page. this will be 1179, 1179, and then I'm gonna have to do question marks here because I didn't record that, but we were starting back at 504. Okay, and I'll leave this up here so I don't forget, because if I don't have it up there, I'm probably going to forget. Alright, jump to chapter 58 and we'll begin. Sockets, fundamentals of TCP/IP networks. This chapter provides an introduction to computer network concepts and the TCP/IP networking protocols. Something that by now in my career I'm very well familiar with, but it's always helpful to review some of the basics. An understanding of these topics is necessary to make effective use of internet domain sockets, which are described in the next chapter. Starting this chapter, we begin mentioning various requests for comment RFC documents. Each of the networking protocols discussed in this book is formally described in an RFC. We provide further information about RFCs as well as lists of RFCs of particular relevance to the material covered in this book. Section 58.7. Internets. An internet network, or more commonly internet with a lowercase I, connects different computer networks, allowing hosts of all the networks to communicate with one another. In other words, internet is a network of computer networks. The term subnetwork or subnet is used to refer to one of the networks composing an internet. An internet aims to hide the details of different physical networks in order to present a unified network architecture to all hosts on the connected networks. This means, for example, that a single address format is used to identify all hosts in the internet. Although various internet networking protocols have been devised, TCP/IP has become the dominant protocol suite, supplanting even the proprietary networking protocols that were formerly common on local and wide area networks. The term internet with an uppercase I is used to refer to the TCP/IP internet that connects millions of computers globally. The first widespread implementation of TCP/IP appeared with 4.2 BSD. Oh, I didn't know that. Does that mean that I thought it was at ARPANET. I thought ARPANET was the place that created TCP/IP. I guess he says widespread, so maybe that's the caveat there. The first widespread implementation of TCP/IP appeared with 4.2 BSD in 1983. Several implementations of TCP are derived directly from the BSD code. Other implementations, including the Linux implementation, are written from scratch, taking the operation of the BSD code as a reference standard defining the operation of TCP/IP. TCP/IP grew out of a project sponsored by the U.S. Department of Defense Advanced Research Projects Agency, ARPA, or later DARPA, with the D for defense, to devise a computer network architecture to be used in the ARPANET. Let me reread this because my mind was wandering. TCP/IP grew out of a project sponsored by the U.S. Department of Defense Advanced Research Projects Agency, ARPA, later DARPA, to devise a computer networking architecture to be used for the ARPANET, an early wide area network. During the 1970s, a new family of protocols was designed for the ARPANET. Accurately, these protocols are known as the DARPA Internet Protocol Suite, but more usually they are known as the TCP/IP Protocol Suite or simply TCP/IP. The web page so-and-so provides a brief history of the internet and TCP/IP. I don't need to read that. Figure 58.1 shows a simple internet. In the diagram, the machine TCP is an example of a router, a computer whose function is to connect one subnetwork to another, transferring data between them. As well as understanding the internet protocol being used, the router must also understand the possibly different data link layer protocols used on each of the subnets that it connects. A router has multiple networking interfaces, one for each of the subnets to which it is connected. The more general term multi-homed host is used for any host, not necessarily a router, with multiple networking interfaces. Another way of describing a router is to say that it's a multi-homed host that forwards packets from one subnet to another. A multi-homed host has a different network address for each of its interfaces, i.e. a different address on each of its subnets to which it is connected. Networking protocols and layers. A networking protocol is a set of rules defining how information may be transmitted across a network. Network protocols are generally organized as a series of layers, with each layer building on the layer below it and to add features that are made available to higher layers. The TCP/IP protocol suite is a layered networking protocol. It includes the Internet Protocol and various protocols layered above it. The code that implements these various layers is commonly referred to as the protocol stack. The name TCP/IP derives from the fact that the Transmission Control Protocol is the most heavily used transport layer protocol. We have omitted a range of other TCP/IP protocols from Figure 58.2 because they are not relevant to this chapter. The Address Resolution Protocol, ARP, is concerned with mapping internet addresses to hardware, e.g. Ethernet addresses. The Internet Control Message Protocol, ICMP, is used to convey error and control information across the network. ICMP is used for the ping program, which is frequently employed to check whether a particular host is alive or invisible on a TCP/IP network. And traceroute, which traces the path of an IP packet through the network. The Internet Group Management Protocol, IGMP, is used by hosts and routers that support multicasting of IP datagrams. The only one I haven't encountered in my life is that IGMP. So you got your network interface hardware, data link, networking layer, transport layer, application layer. All right. One of the notions that lends great power and flexibility to protocol layering is transparency. Each protocol layer shields higher layers from the operation and complexity of lower layers. Thus, for example, an application making use of TCP only needs to use the standard socket's API and to know that it is employing a reliable byte stream transport service. It doesn't need to understand the details of the operation of TCP. When we look at the socket options in section 61.9, we'll see that this doesn't always strictly hold true. Occasionally, an application does need to know of some of the details of the operation of the underlying transport protocol, nor does the application need to know the details of the operation of the IP or the data link layer. From the point of view of the application, it is as though they are communicating directly with each other via the socket's API, as shown in Figure 58.3, where the dashed horizontal lines represent the virtual communication paths between corresponding application, TCP, and IP entities on the two hosts. Encapsulation is an important principle in layered networking protocol. Figure 58.4 shows an example of encapsulation in the TCP/IP protocol layers. The key idea of encapsulation is that the information, application data, and TCP segment or an IP datagram passed from a higher layer to a lower layer is treated as opaque data by the lower layer. In other words, the lower layer makes no attempt to interpret information sent from the upper layer, but merely places that information inside whatever type of packet is used in the lower layer and adds its own layer-specific header before passing the packet down to the next lower layer. The data is passed up from the lower layer to the higher layer. A converse unpacking process takes place. We don't show in Figure 58.4, but the concept of encapsulation also extends down into the data link layer, where IP datagrams are encapsulated inside network frames. Encapsulation may also extend up to the application layer, where an application may perform its own packaging of data. The data link layer. The lowest layer of the Figure 5.8-2 is the data link layer, which consists of the device driver and the hardware interface network card to the underlying physical medium, e.g. a telephone line, a coaxial cable, or fiber optic cable. The data link layer is concerned with transferring data across a physical link in a network. To transfer data, the data link layer encapsulates datagrams from the network layer into units called frames. In addition to the data being transferred, each frame includes a header containing, for example, the destination address and frame size. The data link layer transmits the frames across the physical link and handles acknowledgments from the receiver. Not all data link layers use acknowledgments. This layer may perform error detection, retransmission, and flow control. Some data link layers also split large network packets into multiple frames and reassemble them in the receiver. From an application programming point of view, we can generally ignore the data link layer since all communication details are handled by the driver and hardware. One characteristic of the data link layer that is important for our discussion of IP is the maximum transmission unit, MTU. Data link layer's MTU is the upper limit that the layer places on the size of a frame. Different data link layers have different MTUs. The command netstat-i displays a list of system network interfaces showing along with their MTUs. I don't think that's still a command. That's like old school. What is the new command that replaced netstat dash I? It's IP, right? IP-s statistics link, and then you should see MTU here. I think you can just say IP link, right? IP link, and that has the MTUs as well. Let's see here. So we got our data link layer, IP, TCP application, pretty typical. And our application data is then framed in a TCP frame segment, I guess, which is then put into an IP datagram. Continue on. The network layer, IP. Above the data link layer is a network layer, which is concerned with delivering packets data from the source host to the destination host. This layer performs a variety of tasks, including how many pages is this thing? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We got 12 pages. So that's probably gonna be another hour. Let's try to finish this by 6. I'm gonna speed read it because this is stuff that I have a lot of experience with already. So I'm gonna go real fast here. Let me get some water. All right, speed reading time. Above the data link layer is a network layer, which is concerned with delivering packets data from the source host to the destination host. This layer performs a variety of tasks, including breaking data into fragments small enough to transmit via the data link layer if necessary, routing data across the internet, and providing services to the transport layer. In the TCP/IP protocol suite, the principal protocol in the network layer is IP. The version of IP that appeared in the 4.2 BSD implementation was IPv4. In the early 1990s, a revised version of IP was devised, IP version 6. The most notable difference between the two versions is that IPv4 identifies subnets and hosts using 32-bit addresses, while IPv6 uses 128-bit addresses, thus providing much larger range of addresses to be assigned to hosts. Although IPv4 is still the predominant version of IP used over the internet, in coming years it should be supplanted by IPv6. Both IPv4 and IPv6 should be support the higher. Both IPv4 and IPv6 support the higher UDP and TCP transport layer protocols, as well as many other protocols. Although a 32-bit address space theoretically permits billions of IPv4 network addresses to be assigned, the manner in which addresses were structured and allocated meant the practical number of these available addresses was far lower. The possible exhaustion of IPv4 address space was one of the primary motivations for the creation of IPv6. A short history of IPv6 can be found at layernetworks.com/IPv6.htm. The existence of IPv4 and IPv6 begs the question, what about IPv5? There never was an IPv5 as such. Each IP datagram header includes a 4-bit version number field. Thus, IPv4 datagrams always have the number 4 in its field. And the version number 5 was assigned to an experimental protocol, Internet Stream Protocol. Version 2 of this protocol, abbreviated ST2, is described in the RFC 1819. Initially conceived in the 1970s, this connection-oriented protocol was designed to support voice and video transmission and distributed simulation. Since the IP datagram version number 5 was already assigned, the successor IP4 was assigned the version number 6. Figure 58.2 shows a raw socket type, sock raw, which allows an application to communicate directly with the IP layer. We don't describe the use of raw sockets since most applications deploy sockets over one of the transport layers, TCP or UDP. Raw sockets are described in chapter 26 of so-and-so. One instructive example of the use of raw sockets is the SendIP program, which is a command line driven tool that allows the construction of transmission of IP datagrams with arbitrary contents, including options to construct UDP datagrams and TCP segments. IP transmit datagrams. IP transmits data in the form of datagrams, packets. Each datagram sent between two hosts travels independently across the network, possibly taking a different route. An IP datagram includes a header, which ranges in size from 20 to 60 bytes. The header contains the address of the target host so that the datagram can be routed through the network to its destination and also includes the originating address of the packet so that the receiving host knows the origin of the datagram. It is possible for a sending host to spoof the originating address of a packet, and this forms the basis of TCP denial of service attack known as SYN flooding. Described in details of this attack and the measures used by modern TCP implementations to deal with it. Pretty much anything that is non-authenticated, you can spoof and do like not only flooding attacks, but you can also do like what do they call it? Amplification attacks, potentially. An IP implementation may place an upper limit on the size of datagrams that it supports. All IP implementations must permit datagrams at least as large as the limit specified by the IP's minimum reassembly buffer size. In IPv4, this limit is 576 bytes. In IPv6, it's 1,500 bytes. What is this? I'm not sure what this is. Minimum reassembly buffer size. Okay. IP is connectionless and unreliable. IP is described as a connectionless protocol since it doesn't provide the notion of a virtual circuit connecting two hosts. IP is also an unreliable protocol. It makes a best effort to transmit datagrams from the sender to the receiver, but doesn't guarantee that packets will arrive in the order that they were transmitted, that they won't be duplicated, or even that they will arrive at all. Nor does IP provide error recovery. Packets with header errors are slightly discarded. Reliability must be provided either by using a reliable transport layer protocol, e.g. TCP, within the application itself. IPv4 provides a checksum for the IP header, which allows the detection of errors in the header, but doesn't provide any error detection on the data transmitted within the packet. IPv6 doesn't provide a checksum in the IP header, relying on higher level protocols to provide error checking and reliability as required. UDP checksums are optional with IPv4, but generally enabled. UDP checksums are mandatory with IPv6. TCP checksums are mandatory with both IPv4 and IPv6. Duplication of IP datagrams may occur because of techniques employed by some data link layers to ensure reliability, or when IP datagrams are tunneled through some non-TCP IP network that employ retransmission. IP may fragment datagrams. IPv4 datagrams can have up to 65,535 bytes. By default, IPv6 allows datagrams up to 65,575 bytes, 40 bytes for the header, and then the data, and provides an option for larger datagrams, so-called jumbograms, or jumbo packets is what I've heard them referred to as. We noted earlier that data link layers impose an upper limit, the MTU, of the size of data frames. For example, this upper limit is 1,500 bytes on the commonly used Ethernet network architecture, i.e. much smaller than the maximum size of an IP datagram. IP also defines the notion of the path MTU. This is a minimum MTU on all the data link layers traversed on the route from the source to the destination. In practice, the Ethernet MTU is often the minimum MTU in a path. When IP datagram is larger than the MTU, IP fragments breaks up the datagram into suitably sized units for transmission across the network. These fragments are then reassembled in the final destination to recreate the original datagram. Each IP fragment, need to continue here. Each IP fragment is itself an IP datagram that contains an offset field given the location of that fragment within the original datagram. IP fragmentation occurs transparently to higher protocol layers, but nevertheless, it's generally considered undesirable. The problem is that because IP doesn't perform retransmission, and a datagram can be reassembled at the destination only if all fragments arrive, the entire datagram is unusable if any fragment is lost or contains transmission errors. In some cases, this can lead to significant rates of data loss for higher protocol layers that don't perform retransmission, such as UDP, or degraded transfer rates for higher protocol layers that do perform retransmission, such as TCP. Modern TCP implementations employ algorithms such as path MTU discovery to determine the MTU of the path between hosts and accordingly break up the data they pass to IP so that IP is not asked to transmit datagrams that exceed its size. UDP provides no such mechanisms, and we consider how UDP-based applications can deal with the possibility of IP fragmentation in section 58.6.2. IP addresses. An IP address consists of two parts: a network ID that specifies the network on which a host resides, and a host ID which identifies the host within the network. An IPv4 address consists of 32 bits. When expressed in human readable form, these addresses are normally written in dotted decimal notation, with the 4 bytes of the address being written in decimal numbers separated by dots. When an organization applies for a range of IPv4 addresses for its host, it receives a 32-bit network address and a corresponding 32-bit network mask. In binary form, this mask consists of a sequence of ones in the leftmost bits, followed by a sequence of zeros to fill out the remainder of the mask. The ones indicate which part of the address contains the assigned network ID, while the zeros indicate which part of the address is available to the organization to assign a unique host ID on its network. The size of the network ID is part of the mask. The size of the network ID part of the mask is determined when the address is assigned. Since network ID components always occupies the leftmost part of the mask, the following notation is sufficient to specify a range of assigned addresses. The /24 indicates the network ID part of the assigned address consists of the leftmost 24 bits, with the remaining 8 bits specifying the host ID. Alternatively, we could say that the network mask, in this case, so-and-so, is dotted decimal notation. Boop. An organization holding this address can assign 254 unique internet addresses to its computers. 1 through 254. 2 addresses can't be assigned. One of these is the address whose host ID is all 0 bits, which is used to identify the network itself. Another is address whose host ID is all 1 bits. In this example, which is a subnet broadcast address. Certain IPv4 addresses have special meanings. Special address 127.0.0.1 is normally defined as the loopback address and is conveniently assigned the host name localhost. Oh. Loop device, that's what I wanted. A loop device allows you to treat a regular file as a block device. Commonly used to mount disk images without physical disks, creating a virtual file system in files. Explain what loop devices are again. Okay. I used loop block devices back in 2007, man. almost 20 years ago to do some data recovery stuff for a business. It's my first job out of college. So it's been quite a while. I haven't really used them for much since then. Okay, we were talking about IP addresses, broadcast, loopback address. Yeah. And it's conventionally assigned the host name localhost. Any address on network 127.0.0/8 can be designated as the IPv4 loopback address, but the 127.0.0.1 is the usual choice. A datagram sent to this address never actually reaches the network, but instead automatically loops back to become input to the sending host. Using this address is convenient for testing clients and server programs on the same host. For use in a C program, the integer constant in adder loopback is defined for this address. The constant the constant in adder any is a so-called IPv4 wildcard address. The wildcard IP address is used for applications that bind internet domain sockets on multiple hosts, so on multi-homed hosts. If an application on a multi-homed host binds a socket to just one of the host IP addresses, then that socket can receive UDP datagrams or TCP connection requests sent to that IP address. However, we normally want application on multi-homed hosts to be able to receive datagrams or connection requests that specify any of the host IP addresses. And binding the socket to the wildcard IP address makes this possible. Substitute 3 doesn't specify any particular value for IP adder any, but most implementations define as all zeros. Typically, IPv4 addresses are subnetted. Subnetting divides the host ID part of an IPv4 address into two parts, a subnet and a host ID. The choice of how the bits of the host ID are divided is made by the local network administrator. The rationale for subnetting is that an organization often doesn't attach all of its hosts to a single network. Instead, the organization may operate on a set of subnetworks, an internal internetwork, with each subnetwork being identified by combination of network IDs plus a subnet ID. This combination is usually referred to as an extended network ID. With a subnet, the subnet mask serves the same role as described earlier for the network mask, and we use a similar notation to indicate the range of address assigned to a particular subnet. For example, suppose that our assigned network ID so-and-so, and we chose to subnet this address range by splitting the 8 bits of the host ID into the 4-bit subnet and 4-bit host ID. Under this scheme, that would be 2, 4, 8, it would only be 16 networks of 16 hosts. On this scheme, the subnet mask would consist of 28 leading zeros followed by 4 zeros, and the subnet with the ID of 1 would be designated as so-and-so. Okay. Cool. Network IPv4 address. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8 pages in 30 minutes. Let's do it. IPv6 address. The principles of IPv6 address are similar to IPv4 addresses. The key difference is that IPv6 addresses consist of 128 bits, and the first few bits of the address are a format prefix indicating the address type. We won't go into details of these address types. See Appendix A, so-and-so. IPv6 addresses are typically written as a series of 16-bit hexadecimal numbers separated by colons, as in the following. IPv6 addresses often include a sequence of zeros and, as a notational convenience, 2 colons. Can be employed to indicate such sequence, thus the above address can be written as so-and-so. Only one instance of double colon notation can appear in an IPv6 address. More than one instance would be ambiguous. IPv6 also produces equivalents of the IPv4's loopback addresses, 127 zeros followed by a 1, thus : 1, and wildcard addresses, all zeros written as either 0, : 0, or just : I've seen it as : in order to allow IPv6 applications to communicate with hosts supporting only IPv4, IPv6 provides so-called IPv4 mapped IPv6 addresses. The format of these addresses is shown in figure 58. So it's all 0, then 16, all 1 bits, and then the IPv4 address. I've seen different ranges dedicated to IPv4, so that's just one of them. When writing IPv4 mapped IPv6 address, the IPv4 part of the address, i.e. the last 4 bytes is written in the IPv4 dotted notation. Thus, the IPv4 mapped IPv6 address is equivalent to that, the transport layer. There are 2 widely used transport layer protocols in the TCP/IP suite. User datagram protocol is the protocol used for datagram sockets. Transmission control protocol is the protocol used for stream sockets. Before considering these protocols, we first need to describe port numbers and concept used by both protocols. Port numbers. Task of the transport protocol is to provide an end-to-end communication service to applications residing on different hosts, or sometimes on the same host. In order to do this, the transport layer requires a method of differentiating the application on the host. In TCP and UDP, this differentiation is provided by a 16-bit port number. Well-known registered and privileged ports. Some well-known ports are permanently assigned a specific application known as services. For example, the SSH secure shell daemon uses a well-known port 22. HTTP, the protocol used for communication between web servers and browsers, uses a well-known port 80. Well-known ports are assigned numbers in the range of 0 to 1023 by a central authority, the Internet Assigned Numbers Authority, IANA. Assignment of a well-known port number is contingent on the approved network specification, typically in the form of an RFC. IANA also records registered ports, which are allocated to application developers on a less stringent basis, which also means that an implementation doesn't need to guarantee the availability of these ports for the registered purpose. The range of IANA registered ports is 1024 to 49150. Not all port numbers in this range are registered. The up-to-date list of IANA well-known and registered port assignments can be obtained online at so-and-so. In most TCP/IP implementations, including Linux, port number in the range 0 to 1023 are also privileged. Meaning that only privileged capped net bind service processes may bind to these ports. This prevents a normal user from implementing a malicious application that, for example, spoofs the SSH in order to obtain passwords. Sometimes privileged ports are referred to as reserved ports. Although TCP and UDP ports with the same number are distinct entities, the same well-known port number is usually assigned to a service under both TCP and UDP, even if, as is often the case, that service is available under only one of the protocols. This convention avoids confusion of port numbers across 2 protocols. Ephemeral ports. If an application doesn't select a particular port, i.e. in sockets terminology, it doesn't bind to its socket to a particular port, then TCP UDP assign a unique ephemeral port, i.e. short-lived number for the socket. In this case, the application, typically a client, doesn't care which port number it uses, but assigning a port is necessary so that the transport layer protocols can identify the communication endpoints. It also has the result that the peer application and the other end of the communication channel knows how to communicate with the application. TCP and UDP also assign an ephemeral port number if we bind a socket to port 0, and it specifies the ports in the range 49152 to 65535 as dynamic or private, with the intention that these ports can be used by local applications and assigned as ephemeral ports. However, various implementations allocate ephemeral ports from different ranges. On Linux, the range is defined by and can be modified via the 2 numbers contained in proc_sysnet IPv4 IP local port range. Let's go ahead and cat out proc_sys net IPv4 sysnet IPv4, and then we'll say IP local. Come on. Local port range. So that's the port range for clients. All right. User datagram protocol. UDP adds just 2 features to IP port numbers and a data checksum to allow the detection of errors in the transmitted data. Like IP, UDP is connectionless. I'm not sure why this is in the I guess because it's transport layer. Okay, makes sense. Like IP, UDP is connectionless since it adds no reliability to IP. UDP is likewise unreliable. If an application layered on top of UDP requires reliability, then it must be implemented within the application. Despite this unreliability, we may sometimes prefer to use UDP instead of TCP for the reasons detailed in section 6112. The checksums used by both UDP and TCP are just 16 bits long and are simple add-up checksums that can fail to detect certain classes of errors. Consequently, they do not provide extremely strong error detection. Busy internet servers typically see an average of one undetected transmission error every few days. Applications that need stronger assurance of data integrity can use SSL protocol, TLS, which provides not only secure communication but also much more rigorous detection of errors. Alternatively, an application could implement its own error control scheme. Selecting a UDP datagram size to avoid IP fragmentation. In section 58.4, we described the IP fragmentation mechanism and noted that it is usually best to avoid IP fragmentation. While TCP contains mechanisms for avoiding IP fragmentation, UDP does not. With UDP, we can easily cause IP fragmentation by transmitting a datagram that exceeds the MTU of the local data link. A UDP-based application generally doesn't know the MTU of the path between the source and destination host. UDP-based applications that aim to avoid IP fragmentation typically adopt a conservative approach, which is to ensure that the transmitted IP datagram is less than the IPv4 minimum reassembly buffer size of 576 bytes. This value is likely to be lower than the path MTU. From these 576 bytes, 8 bytes are required by UDP's own header, and an additional minimum of 20 bytes are required for the IP header, leaving 484 bytes for the UDP datagram itself. In practice, many UDP-based applications opt for a still lower limit of 512 bytes for their datagrams. Transmission Control Protocol. TCP provides a reliable, connection-oriented, bidirectional byte stream communication channel between two endpoints, i.e. applications as shown in figure 58.8. Transmission Control Protocol. TCP provides a reliable, connection-oriented, bidirectional byte stream communication channel between two endpoints, i.e. applications, as shown in figure 58.8. In order to provide these features, TCP must perform the task described in this section. A detailed description of all these features can be found in so-and-so. So we've got application A with a socket file descriptor. Application B has its. It has a send buffer and a receive buffer, some state information, and then the networks in between. We use the term TCP endpoint to denote the information maintained by the kernel for one end of the TCP connection. Often we abbreviate the term further, for example, just writing a TCP to mean a TCP endpoint, or the client TCP to mean the TCP endpoint maintained by the client application. This information includes the send and receive buffers for this end of the connection, as well as state information that is maintained in order to synchronize the operation of two connected endpoints. We describe the state information in further detail when we consider the TCP state transmission diagram in section 6163. In the remainder of this book, we use the terms receiving TCP and sending TCP to denote the TCP endpoints maintained for the receiving and sending applications on either end of the stream socket connection that is being used to transmit data in a particular direction. Connection establishment. Before communication can commence, TCP establishes a communication channel between two endpoints. During connection establishment, the sender and receiver can exchange options to advertise parameters for the connection. This is your SYN-ACK dance here. Packaging of data segments. Data is broken into segments, each of which contains a checksum to allow the detection of end-to-end transmission errors. Each segment is transmitted in a single IP datagram. Acknowledgements, retransmissions, and timeouts. When a TCP segment arrives at its destination without errors, the receiving TCP sends a positive acknowledgement to the sender, informing it of a successful delivery of data. If a segment arrives with errors, then it is discarded and no acknowledgement is sent. To handle the possibility of segments that never arrive or are discarded, the sender starts a timer When each segment is transmitted, if an acknowledgement is not received before the timer expires, the segment is retransmitted. Since the time taken to retransmit a segment and receive its acknowledgement varies according to the range of network and the current traffic loading, TCP employs an algorithm to dynamically adjust the size of the retransmission timeout, RTO. The receiving TCP may not send acknowledgements immediately, but instead wait for a fraction of a second to see if the acknowledgement can be piggybacked inside any response that the receiver may send straight back to the sender. Every TCP segment includes an acknowledgement field, allowing for such piggybacking. The aim of this technique, called delayed ACK, is to save sending a TCP segment, thus decreasing the number of packets on the network and decreasing the load on the sending and receiving hosts. Sequencing: each byte that is transmitted over a TCP connection is assigned a logical sequence number. This number indicates the position of that byte in the data stream for the connection. Each of the two streams in the connection has its own sequence numbering. When a TCP segment is transmitted, it includes a field containing the sequence number for the first byte in the segment. Attaching sequence numbers to each segment serves a variety of purposes. Sequence numbers allows TCP segments to be assembled in the correct order at the destination and then passed as a byte stream to the application layer. At any moment, multiple TCP segments may be in transit between sender and receiver. These segments may arrive out of order. The acknowledgement message passed to the receiver back to the sender can use a sequence number to identify which TCP segment was received. The receiver can use a sequence number to eliminate duplicate segments. Such duplicates may occur either because of the duplication of IP datagrams or because of TCP's own retransmission algorithm, which could retransmit a successfully delivered segment if the acknowledgement for that segment was lost or not received in a timely fashion. The initial sequence number, ISN, for the stream doesn't start at 0. Instead, it is generated via an algorithm that increases the ISN assigned to successive TCP connections to prevent the possibility of old segments from a previous incarnation of the connection being confused with segments for this connection. This algorithm is also designed to make guessing the ISN difficult. Sequence number is a 32-bit value that is wrapped around to 0 when the maximum value is reached. Flow control. Flow control prevents a fast sender from overwhelming a slow receiver. To implement flow control, the receiving TCP maintains a buffer for incoming data. Each TCP advertises the size of its buffer during the connection establishment. Data accumulates in the buffer as it is received from the sending TCP and is removed as the application reads data. With each acknowledgement, the receiver advises the sender of how much space is available in the incoming data buffer, how many bytes the sender can transmit. TCP flow control algorithm employs a so-called sliding window algorithm, which allows unacknowledged segments containing a total of up to n, the offered window size, bytes, to be in transit between the sender and the receiver. If a receiving TCP's incoming data buffer fills completely, then the window is said to be closed and the sending TCP stops transmitting. The receiver can override the default size for the incoming data buffer using the SO receive buff socket option. Congestion control, slow start, and congestion avoidance algorithms. How many pages we got here? 15 minutes, and we just got a few pages left, so I can slow down. TCP's congestion control algorithms are designed to prevent a fast sender from overwhelming a network. If a sending TCP transmits packets faster than they can be relayed to the by an intervening router, that router will start dropping packets. This could lead to a high rate of packet loss and consequently serious performance degradation. If the sending TCP kept retransmitting these dropped segments at the same rate, TCP's congestion control algorithms are important in two circumstances. After connection establishment, at this time, or when transmission resumes on the connection that has been idle for some time, the sender could start by immediately injecting as many segments into the network as would be permitted by the window size advertised by the receiver. In fact, this is what was done in early TCP implementations. The problem here is that if the network can't handle the flood of segments, the sender risks overwhelming the network immediately. When congestion is detected, if the sending TCP detects that congestion has occurred, then it must reduce transition rate. TCP detects that congestion is occurring based on the assumption that segment loss because of transmission errors is very low. Thus, if a packet is lost, the cause is assumed to be congestion. TCP's congestion control strategy employs two algorithms in combination: slow start and congestion avoidance. The slow start algorithm causes the sending TCP to initially transmit segments at a slow rate, but allows it to exponentially increase the rate as these segments acknowledged and received by the receiving TCP. Slow start attempts to prevent a fast TCP sender from overwhelming a network. However, if unrestrained, slow start's exponential increase in the transmission rate could mean that the sender would soon overwhelm the network. TCP's congestion avoidance algorithm prevents this by placing a governor on the rate increase. With congestion avoidance, at the beginning of the connection, the sending TCP starts with a small congestion window, which limits the amount of unacknowledged data that it can transmit. As the sender receives acknowledgments from the peer TCP, the congestion window initially grows exponentially. However, once the congestion window reaches a certain threshold believed to be close to the transmission capacity of the network, its growth becomes linear rather than exponential. An estimate of the capacity of the network is derived from a calculation based on the transmission rate that was in operation when congestion was detected, or it set a fixed value after initial establishment of the connection. At all times, the quality of data that the sending TCP will retransmit remains additionally constrained by the receiving TCP's advertised window in the local TCP's send buffer. In combination, the slow start and congestion avoidance algorithms allow the sender to rapidly rise its transmission speed up to the available capacity of the network without overshooting that capacity. The effect of these algorithms is to allow data transmission to quickly reach a state of equilibrium, where the sender transmits packets at the same rate as it receives acknowledgments from the receiver. RFCs. Each of the internet protocols we discussed in this book is defined in an RFC document, a formal protocol specification RFC published by the RFC editor, which is funded by the Internet Society. RFCs that describe internet standards are developed under the auspices of the Internet Energy Task Force, IETF, a community of network designers, operators, vendors, and researchers concerned with the evolution and smooth operation of the internet. Membership of the IETF is open to any interested individual. Following RFCs are of particular relevance to the material covered in this book. Got Internet Protocol by Postel, OG Postel, Internet Standards Subnetting Procedure by Postel and Bogle. We got Transmission Control Protocol by Postel, User Datagram Protocol by Postel, Requirements for Internet Hosts, Communication Layers, Brandon. RFC 1122 extends and corrects various earlier RFCs describing the TCP IP protocols. It is one of a pair of RFCs that are often referred to as the host requirements RFCs. The other member of the pair is RFC 1123, which covers application layer protocols such as Telnet, FTP, and SMTP. Among the RFCs that describe IPv6 are the following. Blah, 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 blah. Internet Protocol v6 by Deering and Hayden. Internet Protocol version 6, addressing architecture. Hinden and Deering again, this time in reverse order. Basic socket interface extensions for IPv6. Gilligan, Thompson, Bound, McCain, Stevens. Advanced sockets APIs for IPv6. Stevens, Thommans, Nordmark, and Jinmai. A number of RFCs and papers provide improvements and extensions to the original TCP specification, including the following: congestion avoidance and control, Jacobson. This was the initial paper described the congestion control and slow start algorithms for TCP, originally published in Proceedings of SIGCOMM 88. A slightly revised version is available at so-and-so. This paper is largely superseded by some of the following RFCs. TCP extensions for high performance, Jacobson again, Brandon, and Borman. TCP selective acknowledgement options, TCP congestion control, TCP congestion window validation, an extension on the selective acknowledgement SAC option for TCP, computing TCP's retransmission timer, the addition of explicit congestion notification, and finally increasing TCP's initial window. I didn't realize Postel had authored the RFC on transmission control protocol, internet protocol, subnetting, and UDP. It's like that's like pretty much all of the basics of networking. Like he authored the RFCs on. I didn't realize that. I understand like he ran the IANA, but like wow, I mean that's just like he basically built the internet. I always thought that this was like work done at ARPA with Vince Cerf and those guys, but Postel is just like he's the author of the RFCs. So, I guess we've got 6 minutes left. Let's read the summary of this chapter, and then that'll set us up for internet domain sockets tomorrow. So summary, TCP/IP is a layered networking protocol suite. At the bottom of the layer's TCP/IP protocol stack is the IP network layer protocol. IP transmits data in the form of datagrams. IP is connectionless, meaning that datagrams transmitted between source and destination hosts may take different routes across the network. IP is unreliable in that it provides no guarantee that datagrams will arrive in order or unduplicated or even arrive at all. If reliability is required, then it must be provided via the use of a reliable higher layer protocol, e.g. TCP, or within the application. The older version of IP is IPv4. In the early 1990s, a new version of IP, IPv6, was devised. The most notable differences between IPv4 and IPv6 is that IPv4 uses 32 bits to represent a host address, while IPv6 uses 128 bits, thus allowing for a much larger number of hosts on the worldwide internet. Currently, IPv4 remains the most widely used version of IP, although in coming years it's likely to be supplanted by IPv6. That did not happen. Or it's still in progress, we'll say that much. Various transport layer protocols are layered on top of IPv4, of which the most widely used are UDP and TCP. UDP is an unreliable datagram protocol. TCP is a reliable connection-oriented byte stream protocol. TCP handles all the details of the connection's establishment and termination. TCP also packages data into segments for retransmission, for transmission by IP, and provides sequence numbering for these segments so that they can be acknowledged and assembled in the correct order by the receiver. In addition, TCP provides flow control to prevent a fast sender from overwhelming a slow receiver, and congestion control to prevent a fast sender from overwhelming the network. Lots of further information on networking that we will not get to. All right. What did I learn from that chapter that I didn't already know? I didn't highlight anything, I don't think. I think all of this is just like review. Yeah, nothing in here was really like anything that I haven't encountered. I guess reading over the list of RFCs, I didn't realize John Postel was the author of TCP, UDP, and IP, and subnetting. It's like, damn, Daniel. But everything else is, some of the congestion control stuff I read through really fast, and there's like so much research and stuff that's went into TCP congestion control and congestion avoidance and flow control and all that stuff. So I feel like this treatment was sufficient. And I didn't really learn much from it, but that's like an area of active research and active implementation that, from what I understand, like it's something that like there's a lot of details there that I'm not aware of and don't really care to learn more about. Trying to think of if there's anything that I don't know already from this. Was just a waste of my hour here. I guess some of the fragmentation stuff I knew about, but like getting really comfortable with like the MTU, the Ethernet MTU being that is one thing, is that I already knew about the Ethernet MTU, and I guess the one thing I did take away from this is that that MTU is generally the smallest MTU for the entire end-to-end networking. Like IP packet size will generally be larger. The maximum size of the IP packet will generally be larger than the MTU of the Ethernet frame. So I guess that's one thing I kind of learned, that the MTU of like the Ethernet is typically the smallest unit. So you want to be slightly below that so that you're not fragmenting your IP packets. I guess, yeah, it was a nice review, but overall I probably could have done without reading it. And that is 6 p.m. So I'm going to mark it here as we are now on page 1197. And it is 6 p.m. Oops. 6 p.m. All right. And if I open up my Python prompt here and jump over to, git status, this thing, vim readme. I gotta go back here. Vim readme. Let's mark that as red. Git status. Git add readme. Git status. Git DC. So we did 3 chapters today. Just a bunch of stuff that's safe to commit. If we git status here, just review the files, make sure they're all C files. No binaries or anything weird. All right, git CI. Finish chapters. It's going to be what chapters? 56, 57, and 58. And we're on 59 now. And if I go under chapter 58, was there anything in here that we did? No. And if you go under chapter 59, was there anything, or 57, I should say. We already did that. Okay, so rm-rf chapter. I'm just gonna tree or LT chapter 58. Just make sure, yeah. rm-r chapter 58. There we go. Wow, 59, 60, 61, 62, 63, 64, 65, 66. Oh no, it's just because of 64. So we got 5 chapters left. All right. I'm gonna cat out my progress here, and we started at page 1149, and we got to 1197. So that's a total of 48 pages we got done today. I would have expected more, but I guess I did take some time writing some programs and stuff. I'm a little bit disappointed with that number, to be honest. I thought it would have been more, but it is what it is. We did do a little bit of experimentation around Unix domains. I did take a really long break for lunch, and I also took a break for an afternoon walk. So yeah, that might have slowed us down some. All right, so tomorrow we'll be starting on sockets for internet domains. This Etsy services file, I mean, I ran into it recently, but I actually haven't really used this much. It's just like all the common services and what ports they're on. Quake. I wonder if Redis is in here. Grep Redis. Yeah, Redis is in there. Postgres. What do I want to do? Like cockroach. Yep. What's something that's a little bit pprof? No, that wouldn't be there. gRPC, semi-gRPC. Trying to think of some things that might be newish, relatively new. There's a lot of stuff in here though, but yeah, I guess that's something that we'll talk about as well tomorrow. Cool. I'll go ahead and wrap there then. So 48 pages. Cool. All right, I'll be on tomorrow. Let me just check my calendar. If I don't have anything going on tomorrow except for training. I do have a thing going on in the afternoon. But I will have time in the morning to do a stream. So I'll get on and I'll read this chapter on internet domains in the morning. Cool. Alrighty.